All right, welcome. So in this video, we're going to talk about kinetic molecular theory, which is topic 3.5. If you want to reference your textbooks, this is in chapter 5, sections 8 and 9 in the TRO textbook. And kinetic molecular theory, that's chapter 5.8. Some of the assumptions we make about gases as we're modeling gas behavior, we assume that the size of the individual gas particles are negligibly small, and that the average kinetic energy of a particle is proportional to the temperature in Kelvin. So the Kelvin temperature is a measure of the average kinetic energy. And we also assume that the collision of particles with each other are elastic, meaning there's no energy loss when they collide with each other. So we don't lose energy to heat or friction. And that in between collisions, the particles do not exert any forces on one another. And these are assumptions we make about what we call ideal kind of gases here. Okay, so now let's take a look more at this whole temperature and kinetic energy and that piece of things. So we're looking at a couple data sets. If you look at this data set, we see a speed distribution at various temperatures. So these are 3 different lines, and we're looking at speed versus number of particles out of 1 million. So these are all the same sample size, and they're all helium. The only difference here is they're at different temperatures. So this one is at negative 100 degrees Celsius, this one is at 100 degrees Celsius, and this one is at 500 degrees Celsius. And what we should notice is that as the temperature increases, this graph shifts over to the right, and it becomes shorter and wider. So we have a wider distribution of speeds at these higher temperatures than we do at the lower temperatures. And we also notice that the average speed is going to increase. So on average, the particles at 500 degrees Celsius are moving faster than the particles at negative 100 degrees Celsius. It is important to notice that that is on average, right? So if you notice over here, there's some subset of helium particles at negative 100 that are actually moving faster than some of the helium particles at 500 degrees. So we should also keep in mind that there is a distribution of speeds here, and the temperature gives us a sense of what the average speed is. And let's look at this graph. So here's another graph that's really similar. To look at the average speed, I would kind of look at where that peak lines up. So here's the average speed at 250 Kelvin. Here's what it is at 500. Here's at 1,000. This is for some unknown gas here, but notice the average speed increases as the temperature increases. But within a certain temperature, not all particles have the same kinetic energy. So there's a distribution here, like at your 1,000 degree curve. Some are moving faster, some are moving slower. And also actually pay attention to your axes. I just realized I talked about speed, but on this graph, the axis is actually kinetic energy. And kinetic energy and speed, they're related, but they're not exactly the same thing. So anyways, within a sample, there's a distribution of kinetic energies. As you increase the temperature, the average kinetic energy increases. And as you increase the temperature, that distribution of energy spreads out. So this is true. You know, these 3 statements are true when we're looking at kinetic energy and also, speed as we increase the temperature there. So now let's look about what happens if we compare samples that have the same temperature. So these are all gases that are all at 100 degrees Celsius, and we're varying the molar mass. So this graph shows several different particles all at the same temperature, but different molar masses. And what we'll notice here is that the lightest molecule, which is helium, has the fastest average speed. So its average speed is somewhere around maybe 1,250 meters per second. And the heaviest molecule, xenon, has the slowest average speed. Its average speed is maybe 200 meters per second. So there's a relationship between the molar mass, like the particle mass, and the particle speed at a given temperature. And here's another graph showing the same thing. Here's a colored graph. In a gas mixture at a given temperature, so in this case, they're all at 25 degrees Celsius, room temperature, the lighter particles are going to travel faster on average than the heavier particles. So that's another observation that we make. And the reason why is it has to do with the relationship between kinetic energy, mass, and speed. So if you look down here, I'm showing it within the context of the equation sheet so that you know where to find it. There's an equation right here, just below the density equation, that tells you the kinetic energy per molecule. So we know that temperature is a measure of the average kinetic energy. And what is kinetic energy? Well, kinetic energy is 1/2 mv squared, where m is the mass and v is the velocity. So this is like the particle mass, and this over here is the particle velocity. So we'll see that when we have two gases that are at the same temperature, they'll have the same kinetic energy, but the one that has the larger mass, the heavier particles, will go slower, and vice versa, the lighter particles will go faster. Okay, so here's a sample problem. This was from near the end of the POGL that we did in class. So it shows us the kinetic energy equation right here. So I've got 4 bottles. They have different gases. They're all at the same temperature. So if they're all at the same temperature, that means that they have we've got the same temp, they have the same average kinetic energy, because the temperature is the measure of the kinetic energy. So for B, which sample has the highest average kinetic energy? They're all the same. Because again, same temp means the same average kinetic energy. However, they're not going to all have the same speed. So to look at the speed, we want to keep in mind that kinetic energy, is 1/2 mv squared. So the one with the smallest mass is going to have the largest speed. So if you look at these particles, you can find the molar masses of them, and it looks like this one's going to have the smallest molar mass. So, you know, a helium atom weighs like 4 AMU, whereas like, you know, CO2 weighs, what is that, 44 AMU, I think is the molar mass of helium, of carbon dioxide. Okay. So these are much heavier. They are going to move slower. My helium particles are the lightest, so they're going to move the fastest. Alrighty. If you look at the gas around you in this room, the air around us in the atmosphere is a mixture of gases, and those gases are all at the same temperature, and they might be 21 degrees. If you're in your house, they might be a little bit warmer or cooler depending on where you are, but all those gases are going to have the same temperature, so they'll have the same average kinetic energy, but they have different average velocities because they have different molar masses. So if you're looking at the gases in this room, here's their temperatures, here's their molar masses. We can predict who would be moving the fastest and slowest on average. So on average, the carbon dioxide molecules will be moving the slowest because they are the heaviest particles. The nitrogen molecules will be moving the fastest because they are the lightest particles. Because again, the kinetic energy is 1/2 mv squared. So this is an equation that we were given just so that we understand the relationship between these variables. We are never going to have to like plug numbers in and solve for a value of kinetic energy. We just need to know the relationship between mass and velocity and kinetic energy. So when you are looking at data, it's really important to pay attention to your axes. Over here on the left, we see a graph that shows the velocity variation with particles that are at a fixed temperature, but with a variety of masses. Over here on the right, we see the velocity distribution for a fixed substance, such as like maybe helium, at a variety of temperatures. So really, when you're doing this graphical interpretation, it's really important to consider what are my axes that I'm being shown. And another application of this would be thinking about the rate of effusion or diffusion. So diffusion is a process by which gas molecules spread out. in response to a concentration gradient. So basically, if like, you squirt some perfume in the corner of the room, it's going to eventually spread out throughout the whole room. That's called diffusion. Those gas molecules spread out. Effusion is very similar, except for the idea is that it would be like you kind of poked a little bit of a hole in a partition and the gas is going to slowly escape through that hole. That's what we call effusion. So there you go. And an example of an effusion application would be, let's say you have a balloon filled with, an air mixture in this room. It's some like high pressure, and there's a small hole in the balloon from which the gas could escape. You might be asked to predict which gas is going to escape the fastest. And we would say, well, I know that nitrogen is going to be moving faster on average than the other molecules will. So it's going to, bump into that hole and pass through that hole in the balloon faster than the other particles, assuming we start with an even number of molecules of each, I should say. But since this one is moving fastest, it's going to kind of escape from that hole the fastest. And so, yeah, so you could make some predictions like, oh, I think that the relative amount of nitrogen is going to decrease faster than the other ones because it's going to leave the balloon faster because it's traveling faster. So that's an example of a effusion application. So let's look at a couple of practice problems here. So let's say we got two containers, they're each 2 liters, and they contain equal number of moles, and they're the same temperature, right? So you've got these 2-liter containers, they're both at 25 degrees. And I find it's helpful sometimes to draw things out. So this has these many moles of helium, this has this many moles of krypton. Is the kinetic energy possessed by the helium greater than, equal to, or less than the krypton atoms? Well, the only information we need for this is the temperature. So the temperature is the same. So when you have the same temperature, you're going to have the same average kinetic energy. You won't necessarily have the same velocity, though. So the helium atoms are going to be lighter than the krypton atoms, right? Helium atoms only weigh 4. And then what is krypton? It's like 131. It's much heavier. Okay. So the helium atoms are going to move faster because they're lighter. The pressure, let's think about how we find pressure. Well, PV equals nRT. Pressure is the moles times the temperature divided by the volume. And they have the same moles, same temperature, same volume. So they're going to have the same pressure. So it doesn't matter that helium is moving faster. It only because they end up with the same temperatures, they have the same average kinetic energy. So it's the kinetic energy that's important in terms of like the pressure, not the velocity so much. Excuse me. Okay. All right, so let's look at one more. So we've got 2 samples again. You've got a liter of helium, you've got a liter of argon. They're both at room temperature. I'm going to call that 21 degrees. And atmospheric pressure, so they're both 1 atmospheric pressure. Let's compare the kinetic energy. Well, if they've got the same temp, they've got the same average kinetic energy. So the kinetic energy is going to be the same, but they won't necessarily have the same velocity. So the heliums, do they have the same average velocity? No, because they have different masses. And we know that kinetic energy is 1/2 mv squared. And we could think of it this way. We could, if we want to do the math here, we could rearrange this and say velocity is going to be the square root of 2 times kinetic energy divided by the mass. If you felt like it, you could rearrange it that way. And then you might say, oh, the ones with the smaller mass are going to give me a larger velocity. And the larger mass are going to give me a smaller velocity. So if this helps, you can rearrange it and think about it that way. Do the argon atoms, because they're more massive, exert a greater pressure on the walls of the container? No, because even though they're more massive, they're also moving slower. So the kinetic energy of the particles is the same because they have the same temperature. So we're just really trying to hit that point home here that the temperatures measure the kinetic energy, which is different from the velocity. And who's going to have the faster rate of effusion? So what we'd have here is the helium is going to have a faster rate of effusion because it is going to have a faster velocity. So what that would mean is, like, let's say we had a sample here that had a mixture of a mole of helium and a mole of argon that were at the same temperature. Our helium is going to escape through this hole faster than the argon will because the helium particles are just moving around faster. So they're going to kind of bump into this hole more often and pass through that space and spread out through this side. All right, so that's it for this video. Let me know if you have any follow-up questions for me.